Hello dear students, this is Professor Anindo Das from Achievers and welcome to my lecture series on second law of thermodynamics. So in the previous lectures, we have dealt with the concepts of engine and refrigerator, the concepts of the Kelvin Planck and Clausius statements, and thereby we have developed the equivalence between Kelvin Planck and Clausius statements. Okay. And we found out a very important parameter, eta. Eta is the efficiency. We found out that eta is equal to mod W cyclic by mod QH, which is again equal to 1 minus mod QC by mod QH. And this is a parameter which varies from 0 to unity. So this much is known to all of us. In today's lecture, we'll be discussing a very important theorem, a legendary theorem in second law of thermodynamics, and that is nothing but the Carnot's theorem. The Carnot's theorem. The Carnot's theorem. So in this lecture, we'll be discussing about the Carnot's theorem. Now, before going into the detailings of Carnot's theorem, at first, we have to have a very clear-cut knowledge about this physical parameter eta. Because Carnot's theorem is somehow related to eta. I am not revealing how. Right now I am not revealing how. That would be revealed with due course of this particular lecture. That will be gradually revealed in this particular lecture. Okay. So in this particular lecture, we'll be dealing with Carnot's theorem, but right now I am not stating the Carnot's theorem. In Carnot's theorem, we would basically reveal a very important fundamental feature in context to the efficiency parameter eta. Okay. So before plunging into this particular theorem, the legendary Carnot's theorem, we must have a clear-cut knowledge about the concept of eta. From the fundamental equation of eta, can you say on which parameters will eta depend? On which parameters will eta depend? Apparently, you can say eta will depend on W cyclic, eta will depend on QH, eta will depend on QC, etc. But actually, eta will not depend on these parameters. Let me repeat it once more. Although apparently it seems that eta depends on mod W cyclic, mod QH, mod QC, etc. But mind it, eta doesn't depend on these parameters. Why? Because it's a ratio. It's a bloody ratio. This is a very interesting fact. Suppose the value of W cyclic is 4 joule and the value of Q cyclic is 16 joule, then the value of eta is 1 by 4. If it is 5 joule and if it is 20 joule, then also it is 1 by 4. So what's the difference? You don't find any difference. So thereby you can say that eta is independent of mod W cyclic and mod QH. So this knowledge must be borne in mind before plunging into the analysis of Carnot's theorem. So in Carnot's theorem, the very first point is on what factors? On what factors will eta depend? On what factors will eta depend? On what factors will eta depend? And my dear students, you have to think out of the box. You have to think out of the box. You don't contemplate into this particular expression. You don't contemplate into this particular expression. You don't contemplate into this particular expression, because this particular expression will not reveal the correct result. Mind it, this particular expression is not going to reveal the correct result. So don't contemplate here. You have to think out of the box. So on what factor eta will depend? You see, it may depend on the working substance. It may depend on the working substance. The working substance you are using to run the engine. Or it may depend on the design. It may depend on the design, or it may depend on TC and TH. So fundamentally, eta is considered to be dependent on the working substance of the engine. It may depend. It may depend on the design of the engine, or it may depend on the temperature of cold and hot reservoirs, that is TC and TH. So eta may depend on these three parameters. But mind it, I have told it may depend, it may depend, it may depend. I am not sanguine about this fact, whether it actually depends on these three parameters or not. But I am just creating some speculations. I am just creating some speculations. So I am quite skeptical about the fact that eta can depend on working substance, it can depend on design, it can depend on TC and TH. Okay, I am not sanguine about that. I am just speculating that eta can depend on the working substance, the design, and TC and TH. So I have used the clause may. It may depend on this. We would analyze it further to understand whether it actually depends on all these three parameters, or one of these three parameters, or two of these parameters, or none of these parameters. So that has to be anticipated over here. Okay. So we will proceed into our next question. So I have answered our first question. I have developed some speculations. Now I'll move on to the second question. Question number 2. Question number 2. If we have two engines, E1 and E2, such that both have different working substance and design, but same TC and TH. So we have considered two engines. One is E1 and another is E2, where working substance, that means parameter A, and design, that is parameter B, These two are different. These two are different. For E1, the working substance is different from that of E2. And for E1, the design is different from that of E2. So A and B are different, but TC and TH, the parameter C is same. This is same. Then what can you say? Then what can you say? If eta depends on all these three parameters, and if you vary two parameters, if you vary this one, if you vary this one, and if you keep this one same, then what is going to happen? Eta will vary, because eta depends on all the three parameters. Out of the three parameters, you are varying two parameters, and you are keeping one parameter same. So obviously eta is going to vary. Obviously eta is going to vary. So obviously, eta E1 shouldn't be equal to eta E2. Obviously, eta E1 shouldn't be equal to eta E2. They will never be equal. They will never be equal. Okay. So this is our second point. This is our second point. Now, here let us consider, let E1 be reversible or irreversible. Let us have both the options. E1 can be reversible or can be irreversible. I don't know. Let us open up both the options for E1. Let us say E1, it can be reversible engine, it can be irreversible engine. It can be a reversible engine, it can be an irreversible engine. So we are not sanguine about the status of E1, whether it is reversible or irreversible. So we are opening up both the options for E1. Let E1 be either be reversible or E1 be irreversible. And let E2 be always reversible. Let E2 be always reversible. Let us consider this situation. Let us consider this situation. So we are considering this situation. This is the considered situation. This is the situation considered. This is the situation considered. This is the situation considered. So what can you say? You see, if we draw the diagram of E1 and the diagram of E2 like this, then this is E1. This is E1 and this is E2. What do you have? For these two engines, you have same TH and same TC. So the third parameter or the third factor on which eta depends remain the same. That means for both the cases TH is same, and for both the cases TC is same. This holds true. And what else you have? You have QH1 amount of heat withdrawn from the hot reservoir and QC1 amount of heat transferred to the cold reservoir, and W cyclic 1 is the amount of work done by E1. And for this case, you have QH2 amount of heat withdrawn from the hot reservoir, QC2 amount of heat transferred to the cold reservoir, and W cyclic 2 is the work done by the system, E2. You have these things. Okay. So A is different, B is different, but C is same. So same TH, same TC. Two different engines, E1 and E2. Now, we must ponder into a very important fact. We know that this E1, it can either be irreversible or reversible. But this E2 is always reversible. So what can you say? You can say that we can always invert E2 to function as R. So we can always invert E2 because as E2 is reversible engine, we can always make E2 work in a reverse direction to function as a refrigerator. This is known to us. If we want to invert an engine into a refrigerator, what is the condition that is necessary to be satisfied? The condition is that particular engine has to be reversible in nature. Now, as E2 is always reversible, so we can always say that we can invert E2 and make it work as an engine, as a refrigerator, since E2 is reversible. Okay, so as E2 is reversible, it can always be inverted into a refrigerator. So, what we'll be doing, see, we will retain E1 as it is. We will retain E1 as it is. QH1, QC1, W cyclic 1. And we will invert E2. We will invert E2. We will invert E2. We can always do that because E2 is reversible. THTC remains all the same. So what we have done, as E2 is reversible, we have reversed its direction. We have reversed its direction and has converted it into a refrigerator. So as E2 is reversible, we have reversed its direction and has converted it aptly into a refrigerator. But I am not sanguine about this process for E1 because E1 has got two options. Either it can be irreversible or it can be reversible. I don't know that. Now, as we are already acquainted with the fact that we can couple an engine with a refrigerator, so obviously we can couple E1 and E2. We can always couple E1 and E2. We can always couple E1 and E2. Let me remind it. Let me remind it to you all. See, I have already told that in case of the lecture for the equivalence between Kp and C, I have already told that we can always couple E and R. We can always couple E and R. Now here E is E1 and R is E2 because E2 has been inverted into the refrigerator. Now, what is the condition for coupling? The condition for coupling is that the magnitude of the cyclic work done by the refrigerator should be equal to the magnitude of the cyclic work done by the engine. So that is the condition. So if we apply it over here, we can say for E1 plus E2 couple, the essential condition is mod W cyclic 1 should be equal to mod W cyclic 2. Mod W cyclic 1 should be equal to mod W cyclic 2. That makes mod QH1 minus mod QC1 to be equal to mod QH2 minus mod QC2. We are already acquainted with these things. Mod W cyclic means mod QH minus mod QC. So this is valid for system 1, that is E1, and also valid for system 2, that is E2. And also, from here we can say that mod QH1 minus mod QH2 should be equal to mod QC1 minus mod QC2. So you can also write this. We can also write this. We can also write this. Reverse is also true. If we take the negative sign, mod of QH2 minus mod of QH1 should be equal to mod of QC2 minus mod of QC1. So the reverse is also true. These two are same equations. And what else we have? Since for these two engines, we have different working substance, different design, but same TC and TH. Obviously, what we have got? We have got eta 1 not equal to eta 2. So we have already got eta E1 not equal to eta E2. We have already got this. We have already got this. Now let us couple things together. Now let us couple things together. So I've got TH, TC over here, E1 over here, E2 over here. E2 functions as a refrigerator. Now mod W cyclic has become all the same. So I'm not putting any suffix 1 or 2. That's quite evident. And it is withdrawing QH1, it is transferring QC1, it is withdrawing QC2, it is transferring QH2. So here E1 is following Kp and E2 is following C. And here none is violated. It's a valid couple. It's a valid couple. None of the two statements are violated. The couple is comprised of two thermodynamic devices, E1 and E2, where E1 follows Kp and E2 follows C, as evident from this particular diagram. Okay. So understood this construction. Now, we have done our point number 2. We have done our point number 2, and we have constructed the couple. Now, our point number 3 is checking Clausius statement for E1 plus E2. Here it is quite expected that as E1 is following Kp and E2 is following C, so E1 plus E2 is ought to follow both Kp and C. Now we'll check this. But before going into this checking purpose or checking process, before going into this checking process, let us ponder into this particular condition. Eta E1 is not equal to eta E2. So you have got two options. You have got two options. Either eta E1 greater than eta E2 or eta E1 less than eta E2. So you have got two options. So let's choose eta E1 greater than eta E2. Let's choose this option. Eta 1 greater than eta E2. So if we choose this option, eta E1 greater than eta E2, then what will we get? Let's see. Eta means mod W cyclic by mod QH. For both cases, mod W cyclic is all the same. But for E1, mod QH is mod QH1. For E2, mod W cyclic is all the same as that of E1. All the same as that of E1. So this is mod W cyclic. And this is mod QH2. Now students, these two terms will get cancelled out. So mod QH2 has to be greater than mod QH1. That means mod QH2 minus mod QH1 is positive. But we already have mod QH2 minus mod QH1 is mod QC2 minus mod QC1. We have already got that also. So here mod QH2 minus mod QH1, this is equal to mod QC2 minus mod QC1. And as mod QH2 is greater than mod QH1, so both these terms, this one and this one, both are positive. We have already got mod QH2 to be greater than mod QH1. And also we have got mod QH2 minus mod QH1 equal to mod QC2 minus mod QC1. So in that way you can say both these two terms are positive. So this is also a very important finding. Okay, so under this constraint, let us check C. So at first, heat withdrawn from the cold reservoir. What is the heat withdrawn from the cold reservoir? What is the heat withdrawn from the cold reservoir? You see QC2 is going away, QC1 is coming. So it's nothing but mod QC2 minus mod QC1. Mod QC2 minus mod QC1. And we all know that mod QC2 minus mod QC1 is positive. So this is positive. As simple as that. As simple as that. Next. What is the work that is being done on E1 plus E2? Here E1 is functioning on E2. E1 is functioning on E2. But there is no external work on E1 plus E2. There is no external work on E1 plus E2. So external work on E1 plus E2 is 0. Is 0. Next. What is the heat transferred to the hot reservoir? Heat transferred to the hot reservoir. What is the heat transferred to the hot reservoir? Again, if you ponder into the diagram, you will see QH2 is going to the hot reservoir and QC2 is coming. So QH2 is going to the hot reservoir and QH1 is coming back. QH2 is going, QH1 is coming. QH2 is going, QH1 is coming. QH2 is going, QH1 is coming. So it amounts to mod QH2 minus mod QH1. And we already know that mod QH2 minus mod QH1 is equal to mod QC2 minus mod QC1. And both are positive. Okay. So it can be analyzed very easily. We have already done this sort of analysis in our previous lecture. Now if we ponder into these results, then we will find some very interesting but contradictory results. What is that? You see, this entity E1 plus E2, what it is doing? It is withdrawing QC2 minus QC1 amount of heat from the cold reservoir, and it is also transferring QC2 minus QC1 heat to the hot reservoir. So it is withdrawing an amount of heat from the cold reservoir, and it is transferring same amount of heat to the hot reservoir, and it is not being supported by any external agency. So E1 plus E2 is violating C. Very surprisingly, E1 plus E2 is violating C. Therefore, E1 plus E2 violates C. Very surprisingly, this couple is violating the Clausius statement. Very surprisingly, this couple is violating the Clausius statement. It should have followed the Clausius statement. It should have followed the Clausius statement. But very surprisingly, we find that this couple is violating the Clausius statement. So we are facing a very sheer fallacy over here. We are facing a very sheer fallacy over here. How this fallacy can be answered? How can you crack this fallacy? That's what Carnot did. And that's why this work of Carnot is considered to be one of the most legendary theories in context to the second law of thermodynamics. Because if this theory was not cracked by Carnot, then it would never have been possible to proceed into the realm of the second law of thermodynamics. Okay, so this theory over here has turned out to be very interesting, and you have to crack the fallacy, and once you crack the fallacy, you can unlock the treasure of the second law of thermodynamics. Okay, so in order to do that, we must proceed into the fourth statement. Fourth point. Now, we haven't made any mistake over here. Still, we are ending up in a very erroneous situation. We haven't made any mistake over here. Still, we are ending up into a very erroneous situation. So what is the reason behind that? Who is going to crack this reason? So if we ponder into this analysis, we'll find the reason. And mind it, students, it is right there written on the board. You have to enhance your observation power so that you can crack this fallacy. You see, we haven't made any mistake. E1 is following Kp, E2 is following C. Okay, everything is okay. ठीक है, everything is okay. But what the mistake is? The sole mistake lies with this approximation. Basically, we have assumed, let us choose, we have chosen this condition. We haven't made any other assumption. This is one of the arbitrary assumptions we have made. We didn't make any other assumption. This is the only arbitrary assumption we have made in order to proceed into this calculation. So obviously, this assumption is wrong. So the reason of violation of C is that this assumption is wrong. Otherwise, everything is correct. So we can say that C violation, it reveals that the assumption eta E1 less eta E1 greater than eta E2 is wrong. This assumption is wrong. Now, if this assumption is wrong, dear students, if this assumption is wrong, that means eta E1 is not greater than eta E2. Eta E1 is not greater than eta E2. So obviously, you have got two options. Either eta E1 less than eta E2. This is option 1. Or eta E1 equal to eta E2. This is option 2. So you have got two options left open. Either eta E1 is less than eta E2 or eta E1 is equal to eta E2. Okay. Okay. Now, let us move on to point number 5. We already know that E1 is either irreversible or reversible, and E2 is always reversible. So you have got two options over here as well. What are the two options? Either the combination is E1, E2, both are reversible, or the combination is E1 irreversible and E2 reversible. So you have got these two options. Either both are reversible. E2 is always reversible. So E2 is always reversible. Now you have got two options. Either E1 is irreversible or E1 is reversible. So either both are reversible or one is reversible and another is irreversible. So let us choose this option. Let us choose E1 and E2 both reversible. If we choose this option, that both are reversible, then what is going to happen? If we choose this option, then what can we do? Then we can do a very trivial mathematics over here. If both E1 and E2 are simultaneously reversible, then what we can do? Here you see, we have reversed the direction of E2 and has transferred it into a refrigerator and has coupled with E1, which is acting as an engine. We have done that. Now if E1 is reversible and E2 is also reversible by default, then we have got another liberty. We can keep E2 intact as an engine and we can reverse the direction of E1. We can keep E2 intact as an engine and we can reverse the direction of E1 and convert it into the refrigerator. So if both are reversible in nature, then what we can do? Then we can keep E2 intact as an engine and we can reverse the direction of E1 and transfer it into a refrigerator and couple it with E2. So just we can replace E1 by E2 and E2 by E1. So we can always do that. So similarly, if we follow the same method of calculation, similarly, if we replace E1 by E2 and E2 by E1, then we can also show that eta E2 is not greater than eta E1. We are just replacing E1 by E2 and E2 by E1. So we can also show that eta E2 not greater than eta E1. So we can also do this thing. So we can also do this thing. By similar calculation, we can do this thing. By similar calculation, we can do this thing. Very simple, very evident. So, we are showing that neither E1 has greater eta nor E2 has greater eta. Neither eta E1 is greater than eta E2 nor eta E2 is greater than eta E1. Then we are just left with the single option, this one. Eta E1 is equal to eta E2. If eta E1 is not greater than eta E2 and also eta E2 is not greater than eta E1, then only we are left with this option. We are left with the option eta E1 equal to eta E2. If this is not the option, if this is not the option, if this is not option 1, if this is not option 1, then obviously it is option 2. Because you are left out with two options. And you don't have option 1 because eta E2 is not greater than eta E1. You directly find that. So you are left with option 1 where you can say eta E1 is equal to eta E2. And this has a great significance. This has a great significance. What is that? If both the engines are reversible, mind it, if both the engines are reversible, then what we are showing? We are showing that, let me check. We are showing that even if the working substance and design are different, and only TC and TH are same, the two eta values are same. They are saying that even if this one and this one are different, only this one is same, the two eta are same. So we can say that for any reversible heat engine, eta does not depend on working substance and on the design. It only depends on TC and TH. Because we have already chosen that E1 and E2 have different working substance. They have different design. So although the working substance and designs are different, yet we are getting same value of eta because we are maintaining same TC and TH. So that means eta reversible only depends on TC and TH. So that means eta reversible is only a function of TC and TH. Eta reversible is only a function of TC and TH. And from here, Carnot's theorem 1 sprouts. Eta reversible equal to function of TC and TH only. This leads to Carnot's first theorem. This leads to Carnot's theorem 1. Carnot's theorem 1. According to this theorem, any two reversible heat engines working between the same temperature difference have same efficiency. If the two heat engines are same, if the two heat engines are reversible, then they will have same efficiency if you just maintain TC and TH to be same. Nothing else will have an impact on the expression of eta or the value of eta if the two engines are reversible. So, according to this Carnot's theorem, you can say that any two reversible heat engines, will have same efficiency when they are made to work within the same temperature difference. If you maintain same value of Tc and Th for two different reversible heat engines, you'll say that they'll have same value of eta. So we have cracked this particular option where both are reversible. Now let us move on to this option. Point number 6. Point number 6. If E1 irreversible and E2 reversible, then what will happen? Then what will happen? See, if you have chosen this option, where both were reversible, you have already locked option 2. That means this option corresponds to option 2. This choice rather, both E1 and E2 reversible, this choice corresponds to option 2. So the only way that is left out is this choice must correspond to option 1. This choice where I am choosing E1 to be reversible and E2 to be reversible, this choice must correspond to option 1. So this choice, E1 irreversible and E2 reversible, must correspond to option 1. And what option 1 says? That is, you see, eta E1 less than eta E2. You see, what is option 1 saying? Eta E1 less than eta E2. So eta E1 less than eta E2. And from here, Carnot's second theorem sprouts. From here, Carnot's second theorem sprouts. Carnot's theorem 2. What is that theorem? You see, if E1 is irreversible, it has lower eta. If E2 is reversible, it has higher eta. So any reversible heat engine is always more efficient than an irreversible heat engine. Any reversible heat engine is always more efficient than an irreversible heat engine. That means reversible heat engine has maximum efficiency. So any reversible heat engine is always more efficient than an irreversible heat engine. Any reversible heat engine is always more efficient than an irreversible heat engine. So far, what we have found, let's see. In a single line we can write. See, general expression of eta is mod W cyclic by mod QH. This is again equal to 1 minus mod QC by mod QH. This is what we obtain from the Kelvin-Planck statement. And we have shown that the general eta is either equal to or less than eta reversible, which is a function of Tc and Th. When it is less than, if it is irreversible. If the process is irreversible, then eta is less than eta reversible. Because we know that any irreversible heat engine is always less efficient than a reversible heat engine. So eta reversible is always greater than eta irreversible. So if the process is irreversible, the sign is less than, because for irreversible engine, eta irreversible is less than eta reversible. But if it is reversible, then the sign is equal. Okay. So this was Kelvin-Planck statement, and this was Carnot's theorem. So this is the combination of Kelvin-Planck and Carnot's theorem. This is the combination of Kelvin-Planck and Carnot's theorem. This is the combination of Kelvin-Planck and Carnot's theorem. So that's all, students, for today's lecture, and we have depicted the meaning of Carnot's theorem and the theorems that has already been deduced over here. So this is a very important topic, and in the next class we'll move on to Carnot cycle. So bye bye for now. Have a nice day ahead.